Problem we're going to look at today is question 5.48 out of Fundamentals of Heat and Mass Transfer by Bergman and Levine. The problem is given to us as follows. It says, referring to the semiconductor processing tool of problem 513, it is desired at some point in the manufacturing cycle to cool the chuck, which is made of aluminum alloy 2024. The proposed cooling scheme passes air at 20 degrees Celsius between the air supply head and the chuck surface. The schematic is provided. We're asked to solve two problems. The first one says, if the chuck is initially at a uniform temperature of 100 degrees Celsius, calculate the time required for its lower surface to reach 25 degrees Celsius, assuming a uniform heat convection coefficient of 50 watts per meter squared Kelvin at the head chuck interface. The second question is to generate a plot of time to cool as a function of the convection coefficient for the ranges of 10 to 200 watts per meter squared Kelvin. If the lower limit represents a free convection condition without any head present, comment on the effectiveness of the head design as a method for cooling the chuck. So the first thing is we'll collect all of our knowns and then list the problems that we want to find. So what we're given is we know that the chuck is initially at 100 degrees Celsius and the air coming in from the cooling head is at 20 degrees Celsius. We're also given a uniform heat transfer coefficient of 50 watts per meter squared Kelvin, as well as an L or length of the cooling chuck of 25 millimeters. The properties of aluminum 2024 can be assumed to be the K thermal conductivity of 177 watts per meter Kelvin, the density rho of 2,770, and the specific heat capacity to be 875 joules per kilogram Kelvin. In problem A, we're asked to find the time required for the bottom of the chuck to reach a temperature of 25 degrees Celsius. And for problem B, we want to plot that time to cool for convective heat transfer coefficients of 10 to 2000 watts per meter squared Kelvin. So our schematic looks like this. We have a cooling head that comes down and air is supplied in a jet, which passes over the heated chuck. We have our chuck on the bottom here, which is 25 millimeters tall. And we're told that the bottom side is insulated, so we'll assume that's adiabatic. Some assumptions that we can make about this problem. The first one is we'll assume that it's semi-infinite in two directions. So in and out of the page, as well as left and right on this page, we're going to assume that this plate is very big, and therefore the conduction is only one-dimensional. We'll assume that the thermal properties of the chuck and the air do not change with temperature. And we'll also neglect radiation. The final assumption we're going to make is that the uniform heat transfer coefficient of 50 watts per meter squared Kelvin is going to be uniform across the entire chuck. So to solve this problem, we'll start by making some dimensionless numbers. So we'll first non-dimensionalize the temperature as theta star, and that's going to be T x of T minus T infinity or T ambient over T initial minus T ambient. We'll also non-dimensionalize the length parameter as x star, which is just going to be x over L. So x over the 25 millimeters. So since this is 1D conduction through a planar wall, we're going to use the first term approximation to solve this problem. So the exact solution is going to be given as follows. It's going to be theta star is equal to C1, which is a constant, times E to the negative zeta 1 squared, over alpha T, alpha being the thermal diffusivity, times time over L squared. And that's all going to be multiplied by the cosine of zeta 1 to the x star. So since we're going to solve for time, which we can get out of the Fourier equation here, we can rearrange our equation and solve for T. And our equation will become T is equal to the natural log of theta star over C1 cosine zeta 1 x star times L squared over zeta 1 squared alpha. So we now have to solve for some of our input parameters. The first one, we can plug in our numbers that we were given in the problem, and we can come up with the theta star value, which is going to be 0.0625. We can also assume what the zeta 1 value is going to be, or we can approximate it by simply taking the square root of the BO number, which is going to be the square root of HL, which is the heat transfer coefficient times the characteristic length, over the thermal conductivity K. And that's going to give us a value of 0.084036. Since we want the temperature at the bottom of the plate, we'll assume that x star is equal to 1, our non-dimensional length. And then we can also calculate C1, which is our first coefficient of our infinite series. And that's going to be equal to 4 sine zeta 1 over 2 zeta 1 plus sine 2 zeta 1. And that's going to give us an approximate value of 1.001176. We can then take all of our numbers and plug it into this t equals equation. And that's going to give us that the time for the bottom surface to reach 25 degrees Celsius is going to be about 3,363.08 seconds, or approximately about 56 minutes. For problem B, we're asked to find how long it will take for the chuck to cool with a given heat transfer coefficient from 10 to 2000. So again, we can reuse our theta star from the previous problem, as well as our x star value, because we're still going to be looking at the bottom surface. We're going to have to calculate two parameters depending on the heat transfer coefficient. So we'll start by calculating our zeta 1. And again, zeta 1 is going to be dependent on h, or our heat transfer coefficient. So we're going to have to solve this at each point in the graph. And we can also calculate our C1 for each condition, which is going to take our zeta 1 and plug it into this equation. With those two solved at each heat transfer coefficient, we can then solve the equation for time at any point by plugging in the zeta 1 and C1, and again, take the first term approximation. So on the graph on the left here, we can see that our time to cool is plotted on a log scale, and our heat transfer coefficient is on the x-axis down here. And we can see as we increase the heat transfer coefficient, the time that it's going to take to cool the chuck is going to drop fairly dramatically. To calculate this plot, we used a MATLAB script, which I'll look at now. So the MATLAB script that we created for this problem, we started by plugging in all of our parameters. So we have our initial temperature, our fluid temperature, the T final, which is the temperature that we'd like to reach, our characteristic length, which is the 25 millimeters, as well as our calculated theta value. We can also input our material properties for 2024, including the thermal conductivity, the density, as well as the specific heat. And we'll just quickly, at the top of the code here, calculate alpha, or our thermal diffusivity. Next, we can go ahead and define our heat transfer space that we're going to define it over. So we're going to use a line space, or Lin space, and go from 10 to 2000 watts per meter squared Kelvin, and we're going to take 100 points. As stated, we need to calculate our BO number as well as our C1 for each of these data points. So we'll start by calculating the BO number with HL over K, and this is going to give us an array of 100 points. We can use that BO number and the approximation of the square root of the BO number to be zeta, and calculate that as well. And then finally, our estimation of C1 by plugging in our calculated zeta value. We'll then pre-allocate our time array. So we'll set t is equal to 0s times the length of h, so that 100 that we put in the h equation, and then comma 1, so we just get a one-dimensional array. We're then going to loop over each h value. So we'll start with I is equal to 1 to the length of h. So it's going to loop over all 100 points. We'll set two parameters, which is going to be our zeta new and c new. And we're just going to pick out the zeta value and c value that we calculated in the arrays above. And then we'll plug those in for the specific heat transfer coefficient at that point and come up with the time that's given to us with the corresponding heat transfer coefficient. So when we run the code, we will get all of our arrays, and then we can simply plot our array versus the heat transfer coefficient by just using the plot function. And we'll use this set GCA y scale equal to log to plot our y-axis on a log scale, which can make it a little bit easier to look at this graph. And so with that, we've solved the problem, and we can now comment on how the chuck is going to cool depending on the heat transfer coefficient. And what we can see is that if we increase the heat transfer coefficient, likely by increasing the amount of mass that we're pushing through the jet, which is being used to cool, we can actually make a significant impact in the cooling time of that chuck. So depending how fast we need to cool the chuck, we may need to get our heat transfer coefficient quite high to get it to a reasonable value.